Pascal. 1 Pascal is equivalent to 1 Newton per meter squared, and it is also measured in bar. 1 bar is equivalent to 10 to the power 5 Newton per meter squared, which is also equal to 10 to the power 5 Pascal. Pressure is a scalar quantity, that is, it has magnitude but no direction. It has magnitude but no direction. As we continue, we are going to consider some important characteristics of liquid pressure. Number 1, liquid exerts pressure in all directions. Number 2, the pressure at all points at the same level within a liquid is the same. The pressure at all points at the same level within a liquid is the same. Number 3, the pressure in a liquid increases in direct proportion to the depth of the liquid. Then number 4, the pressure in different liquids at the same depth varies directly with density. So these 4 characteristics are very important, and those are the characteristics of liquid pressure. If we are to consider the 4th characteristics, the pressure in different liquids at the same depth varies directly with density. So from there we can have pressure to be equal to the density, okay, multiplied by acceleration due to gravity multiplied by the height. All this has a value, and if you like, you can put it, the density can be your normal D, G, H. But this one is a particular symbol used for density. You call it rho. And that's the symbol. So that you have this or you have D, it's still the same thing. So from there, if we are to consider this formula for pressure, our D, which is the density, is referred to the density of the liquid. Our G is the normal acceleration due to gravity, and our H is the height of the column of liquid, the height of the column of the liquid. And we can have what we call the pressure of the liquid, or the pressure at the surface of the liquid. We call it P naught, because there are sometimes we'll be looking for the pressure. It will be equal to the P naught plus the normal pressure, where our P naught is referring to the pressure at the surface of the liquid. Our P naught is equal to the pressure at the surface of the liquid. Okay? We are going to consider a question to buttress this formula to see how it works. Okay? Then from there, we are still going to consider some useful application of pressure. It is applicable in rubber soccer. Okay? You know rubber soccer. It is also applicable in drinking straw. That straw we use to drink and we insert inside the bottle. Drinking straw. That is also applicable in pipettes or pipettes. Okay? Those are the useful application of pressure. Then we are going to consider Pascal's principle. Pascal's principle states that the pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and the walls of the containing vessel. And that is the Pascal's principle. And we have the application of Pascal's principle in the car brake system. Okay? And it is also applicable in hydraulic press. Car brake system and hydraulic press. And that one we are going to consider that of hydraulic press to solve some questions. But before we go into that, let's see how it works. So let's now take hydraulic press to illustrate Pascal's principle. Pascal's principle is illustrated by the means of hydraulic press. Let's consider the diagram. This is a press, and this press consists of two cylinders. You can see it. You have one cylinder of a particular diameter, another cylinder of a particular diameter, cylinder half and cylinder X of different diameters, as I've said. Then the cylinders filled with water, it can be filled either with water or with oil. So this is oil. In this case, we have oil. Okay? The cylinders can be filled with water or with oil, and the two cylinders are joined with a connecting tubes. This is the tubes. Okay? As shown in this figure. Then we have what we call a piston. A tight piston is fitted in each cylinder. This is a piston. The role of this system is the piston. Okay? This is another piston. We have a piston for the one with the smaller diameter and this one with the bigger diameter. Okay? This has a piston. The piston of small cross-sectional area, let's call it A1. Because this is the one with the small diameter. Let's call it A1. This is the piston. Okay? Then the piston for a bigger one, let's call it A2. That is the area for the diameter. Then after we have done that, the tight piston is fitted in each cylinder, as you can see on the board. Then the piston of small cross-sectional area A1 is used to exert a small force F directly on a liquid such as the oil we are having here now. So by the time we have a piston, if you use the piston to press it down, downward force, when you force it downward, what will happen to this liquid? The liquid will flow from the cylinder of small diameter, it will rush to the other side. Okay? And if you do the same thing to the piston of a bigger diameter, it will also do the same thing. Okay? So what can we derive from there? Let us assume we exert a pressure on this cylinder of a smaller diameter, and as I have defined pressure as force over area. You apply a force, small f, over the area, because you apply a force on a particular area which is on the area of the cylinder, the small cylinder half. Then we have A1, because force we go force over what? Over area. Okay? And then that's one thing we are going to get. Then as we all know that once the pressure is the same in all directions, that I mean the pressure is the same in both cylinders, you can also have for the bigger cylinder that the pressure will be written, can also be written as small f over the area A2. Since P is equal to this and P is equal to this, you can have F over A1 is equal to over what? A2. Okay? Let's make our F the subject of the formula. Okay? F A1 is equal to F A2. Let's multiply. So that F, capital F, will now be equal to F A2 over A1. Okay? Then finally, F over small f will now be equal to A2 over A1. And that's where we are going. What is the value of a capital F? Our capital F there is the force exerted on the larger cylinder over the small force exerted on the smaller cylinder. Then we have A2 to be the area of the piston for the larger cylinder. Then A1 is the area of the piston on the smaller cylinder. And we can use this to solve some problems. And this is all about hydraulic press. This is all about the hydraulic press. Then we are going to consider some questions. Question number 1. The normal atmospheric pressure at sea level is 10 raised to the power 6 Newton per meter squared. If the atmosphere has a uniform density 2 kilogram per meter cube, find the height of the atmosphere. Find the height of the atmosphere. Let's take it one by one. The pressure is equal to 10 raised to the power 6 Newton per meter squared. Then we have the density to be equal to 2 kilogram per meter cube. That is the value we are given. Then we are looking for the height of the atmosphere. Remember we said density P is equal to the density as related to gravity and the height. Okay? But we are given the value for pressure. The pressure is 10 raised to the power 6, which is equal to, we are given the value for density, which is 2. The value for our G is 10. Then we are looking for what? Height. 10 raised to the power 6 will be equal to, this is 20. Okay? So that if you divide both sides by 20, we are going to have our h, which is the height, 10 raised to the power 6, divided by what? 20. And this is equal to 10 raised to the power 6 will give us 1 million, that's 60, divided by 20.